Hi everyone, this is Mahmoud Ammar, PhD researcher at K. Leuven. Today I'm gonna present my paper Verify and Revive Secure Detection and Recovery of Compromised Low-End Embedded Devices. Needless to say that everyone nowadays can see the digital transformation in every aspect of our life. Millions of embedded devices are already deployed in various scenarios, including the most critical ones. These devices are becoming attractive targets for a wide variety of cyber attacks. Normally, they are optimized for low cost, low power, and small size, so they are not really expected to have sophisticated security mechanisms. Therefore, remote attestation is emerged as a distinct and cheap security service that allows a trusted party, called a verifier, to check the software integrity of a remote and trusted embedded device that we call a prover. It is implicitly assumed that the verifier has a snapshot of the prover's memory to decide after running the remote attestation protocol whether the prover is compromised. In the last 2 decades, various remote attestation protocols have been proposed. They can be classified to either hardware-based, software-based, or hybrid. Each category has pros and cons. However, the vast majority of them share two main limitations. First, all remote attestation protocols are vulnerable to the time for check time fuse attacks. By means of a transient malware can infect a device, it would perform its malicious task and leave without being detected, as this could happen between any two consecutive remote attestation routines as visualized in this figure. The second limitation is that most of the remote attestation protocols don't really look beyond detection. They don't provide any means to recover or at least heal the compromised embedded device by erasing the detected malware. They assume manual healing or recovery will be done after reporting the result. This is of course a very costly assumption and not always valid in some scenarios. These are two main limitations. However, we would like to highlight two minor related ones, which are the privacy and nature of devices. By privacy, we mean, is it possible that the verifier can attest the prover without having any clue about its memory or software? In many scenarios, verifiers are trusted but also limited devices, and accordingly, they can't keep a snapshot of the memory of nearby provers. While this is also related to the nature of devices, current remote attestation protocols don't provide or don't consider this with respect to prover devices. The ones that would give strong security guarantees can't really be applied to all devices, even though hybrid ones can be accommodated on low-end devices, but not all of them. So, this slide would formulate our problem statement. We really are looking for a remote attestation protocol that would be TOCTOU-secure, that would just like consider some kind of automated healing. It would be ideal if it considers semi-automated or automated recovery as well of cleaned or healed but non-functioning devices. Also, we are looking for some kind of flexible protocol that would just like, in addition to be efficient in robust, reliable, it would just like consider also like low-end embedded devices. To address the aforementioned issues, we propose Verify and Revive, a pure software security service that provides strong security guarantees. We design it to just work on very resource-constrained devices that have zero hardware security features. Verify is a TOCTOU-secure remote attestation schema with a built-in secure erasure module that is automatically executed as a countermeasure in case of detecting malware infection on the corresponding prover. On the other hand, Revive is a secure code update schema that is executed upon request to install regular updates or as a recovery technique to restore the last benign settings of the cleaned yet non-functioning prover. Before diving into the details of Verify and Revive, we would like to clarify our adversary and networks models. For the attacker model, it's just like similar to all existing hybrid schemas. We consider all remote attacks by all means. We rule out physical and DOS attacks. In case of for the specification of devices, we don't really consider DMA-enabled devices. And also we assume that our architecture is initially deployed by a trusted party. In terms of networks, we do support two kinds of networks, or we support like more networks than a traditional remote attestation protocols, considering that the verifier would be a limited but trusted device, and accordingly it can't really have like any clue about the prover's memory. This could be, of course, in this scenario could be even in like industrial networks or even in smart home networks as well. Okay, now the main challenge is how to initiate trust. A root of trust is necessary to establish any security service with strong security guarantees. Of course, this is typically attained with memory isolation or software isolation, which is a key enabling property for all kinds of software integrity and confidentiality mechanisms. Given that we talk about simple devices where software run as a bare metal in single address space, we have to isolate portion of this memory for the trusted computing module. For this purpose, we employ a software-based memory isolation technique called the Security MicroVisor. Using it, the memory of the device looks like as what you see in the figure. This technique is a variant of the software fault isolation approach. In other words, the Security MicroVisor initially requires deploying the trusted software module by a trusted party along with the secret keys on a predefined area of the memory of the corresponding device. It then uses selective software virtualization during the compilation time and instruction level code verification on the device itself to check that the deployed and trusted software can't really read or write the protected memory area. It can't even execute it except for the selected entry point. It's important to mention that we did like some extension to this memory isolation technique to be able to securely tackle the TOCTOU attacks. We refer to the paper for more details about this. Also, for further details about how the isolation mechanism exactly works, we refer to the associated publication of it that you can see in the slide. Leveraging the Security MicroVisor, the architecture of Verify and Revive is shown in the figure. Verify and Revive are deployed as two trusted software modules on the top of Security MicroVisor. The untrusted software can only interface with either Verify or Revive. It has to invoke, of course, Verify to run the remote attestation routine upon receiving an attestation request. On the other hand, it can also invoke Revive to either run authenticated updates or to maintain the feature of self-updating code by writing or erasing portion of its memory through the underlying security microvisor. Of course, the underlying security microvisor primitive will do so if the operation is safe with respect to the protected memory area. This is the pseudocode of Verify. It behaves exactly similar to any hybrid schema. Of course, it's just like interactive protocol where the verifier sends an authenticated request to the prover just like to run the remote attestation routine and send its attestation report. Both the verifier and the prover share a secret key for authentication and two counters. We are mostly concerned about CT, which is like the counter that we added to detect like TOCTOU attacks, leveraging the power of the security microvisor which controls all writes to the memory. So whenever the untrusted software invokes the security microvisor to update anything in its memory, this will increase the value of CT and this value will be injected in the attestation report. The verifier doesn't have to know anything about the prover's memory. After authenticating the attestation report, it can consider the prover compromised if either the value of the report is 0 or CT is not as expected. Of course, thanks to the formally verified properties of the entire architecture that preserve functional correctness of the code. By the way, please note that CT is increased when updating memory locations that are not really supposed to be touched or changed during some period. Further details are in the paper. And of course, in case of detecting malware, an automatic secure erasure module will be fired to erase the unprotected memory area as shown in the new figure. As said previously, Revive can be run to either perform regular updates or to recover non-functioning devices. This technique preserves integrity, confidentiality, and authenticity as well of the software to be deployed. The network operator and the prover would only know about the semantics of the software. All parties, including the verifier, can't really decrypt the deployed image. This technique is designed to be even lightweight, adhering to the to the Internet Engineering Task Force specification for Class 1 IoT devices. In terms of implementation, the Verify and Revive architecture is implemented on the MicroBnB platform that accommodates like an EVR microcontroller and use a low-range radio transceiver for wireless communication. We also considered using two formal verified cryptographic primitives from the Hackle library for authentication and encryption and decryption as well. Of course, for authenticated integrity verification and encryption and decryption. In terms of evaluation, one of the unique features of Verify and Revive is that it is resistant to remote physical destructive attacks that targets wearing of the flash memory. The counter CT is designed to be 8-bit counter, so after 255 times of invocation for writing, it will not be set again until the operator allows this. So he would have some knowledge about what's going on in the device itself in order to prevent such kind of attacks. And by the way, those attacks have been already seen in computer systems and smartphones as well. This table shows the flash memory utilization. Our architecture consumes around 11 kilobytes from flash memory. This is the only price that we have to pay to assure the security and activates this bunch of security services. This is another table that would show that deploying secure images would never consume more than 4.6% of overhead on top of the size of the real image, considering 4 different types of application as a benchmark. And this is what this in terms of time overhead of deploying these 4 images using different configurations, and the worst case scenario would just never exceed 8%. In terms of execution time, since this is something really correlated with the battery lifetime, we showed that running Verify and Revive is really very efficient as an impact on the battery itself, and the battery would last for more than 5 years after if running the attestation routine every 2 hours or more. So to conclude, Verify and Revive is really the first and only software security architecture that features rich security services while providing strong security guarantees. We thank you for attending my presentation, and I would like to answer any question during the live question and answer session.